In this lecture and the next lecture, I will be talking on furnace efficiency, fuel saving and carbon credit. The concept of carbon credit is also known as carbon offset and also carbon trading. Whatever I have covered in the last lectures on fuels, furnace and refractory, I will be using all the contents of the lectures to illustrate the concepts over here. So, let us first of all consider the furnace efficiency. Now, for that let us consider a fuel fired furnace. Let us consider a fuel fired furnace which is operating at temperature Tu. We will also consider Tu is the furnace temperature as well as the product temperature, and this temperature is attained by combustion of fossil fuel. As we all know, on combustion, potential energy of the fuel is converted into sensible heat of the products of combustion at adiabatic flame temperature. Now, this heat is transferred to the walls of the furnace and to the product which is used for heating, and after completion of the heat transfer, the products of combustion exit the furnace. So, let us take the H in is the heat input, at temperature TAFT, which is the adiabatic flame temperature. Let us take HPOC is the heat taken by products of combustion on exit. A fraction of the heat is also lost through the walls of the lining. So, let us consider HL is the heat loss through the walls of the lining, Now, it is also important to tell the quality of the heat which depends on temperature, and let us see that HPOC, heat taken by POC on exit, is at temperature TPOC, and the heat loss through the walls of the lining is at TL. So, the product also carries with them heat, and let us take HU is the heat carried by the product at temperature Tu. So, the same thing now we can represent in the form of a diagram that will clear. So, this is the furnace chamber, this is somewhere here the lining, so this one from here to here, this scale, let us consider this is heat input, this one is the heat input, we are nomenclating HIN at temperature TAFT, which is the adiabatic flame temperature. Now, as we have done in problems on combustion and heat utilization and heat transfer so on, we have seen that a fraction of the heat is lost with the products of combustion, and this is a major fraction. So, this heat which is the HPOC, which is lost at temperature TPOC. Now, the sum of the heat is taken by products of combustion by product which is HU at TU, and this is the amount of heat which is lost through the walls of the lining HL at temperature TL. Now, this is typical a Sankey diagram or a energy flow diagram which is used to illustrate the flow of energy in a system. So, you are seeing here a constant amount of energy is in and it is utilized to heat the product. The product carries the heat equal to HU at temperature TU, fraction of the heat is lost which is HL, and another fraction is carried by the products of combustion. So, now if you write down steady state heat balance, at temperature TU and constant fuel input and it is here the mentioning of the temperature is important, because once the furnace attains a steady state, the furnace operates at temperature TU, which is attained by the heat transfer from the products of combustion at TAFT, that is adiabatic flame temperature. A fraction of the heat is lost through the products of combustion and so on as shown in the figure. So, that means, if we alter the adiabatic flame temperature by altering the fuel input, then this balance will be disturbed. So, that is where it is important to say that this steady state heat balance is done at constant temperature of the furnace. So, by mentioning constant temperature of the furnace, it is automatically meant that the temperature or the adiabatic flame temperature is also a constant, that is fuel input is constant and so on and so forth. So, that is where this is important to say that steady state heat balance at constant temperature of the furnace. So, if you do that, then H in, that is equal to HPOC plus HU plus HL plus other losses, which at the moment we are ignoring. Other losses could be, say, from the hearth, bottom of the hearth, to the cooling water, to the opening door. These are all the, say, the additional losses which are there. Now, we define, say, for example, if we divide by H in, so let us take this is equation 1. We divide the whole equation by H in and rearrange the equation, then we will get HU upon H in, that is equal to 1 minus HPOC upon H in minus HL upon H in minus H other losses upon H in. Let us say this is our equation number 2. Now, if we define, so let us define the thermal efficiency of the furnace. Thermal efficiency of the furnace. Now, thermal efficiency of the furnace is defined in terms of the ability of the furnace to heat the product or to do the useful work. So, the thermal efficiency we define, say, this thermal efficiency we define, that is equal to energy absorbed by the product divide by energy input. In this definition, we are evaluating the performance of the furnace in terms of its function. For example, in this particular heat balance, the function of the furnace was to heat the bloom, billet or slab or whatever the case may be. So, the thermal efficiency, that is equal to 1 minus HPOC upon H in minus HL upon H in minus H others upon H in. This is the thermal efficiency of the furnace. So, you note from this equation that thermal efficiency of the furnace can be increased by reducing the heat loss through the walls of the lining, that is H L upon H in, and by reducing the losses, say H others upon H in, for example, reducing the opening losses or through the hearth or through the cooling water and so on. Once the temperature of the furnace is TU, then HPOC upon H in has become a constant value. So, the increase in thermal efficiency can be achieved only by decreasing either the wall losses or other losses. So, that is the one thermal efficiency. Now, in some cases, sometimes the efficiency of insulation can also be assessed. That is, you have made a furnace chamber by a lining of certain thickness of certain thermal conductivity. So, here efficiency of a furnace, efficiency of the furnace can also be evaluated, by the effectiveness of insulation, So, here this efficiency this is called as furnace efficiency. Or you can also call as this particular parameter evaluates how effective the insulation is to retain the heat in the furnace. So, that is equal to energy in minus heat loss. Now, remember, when I say heat loss, that means is through the lining of the furnace. The heat taken by POC is not considered to be loss, because it is the inherent feature of the energy achieved by combustion of fuel. So, that is not the heat loss which is carried by the HPOC, that has to be there. So, when you say heat loss, that means heat loss through the lining upon energy in into 100. So, ultimately this becomes 1 minus H L upon H in. So, this is the furnace efficiency. Now, note that the furnace efficiency is very much greater than thermal efficiency, as I will show in a problem which I will be taking immediately after this particular lecture. Now say let us consider that we install a preheater. Say we install a preheater. And preheat the air So, now what we are doing, for example, this is the furnace, This is the furnace. Here HPOC is out, it is taken into the heat exchanger. This is heat exchanger. This is again out, and from here, say we are having here fuel input, and this is the sensible heat in air, sensible heat in air. And if say epsilon is the efficiency of preheater, if epsilon is the efficiency of preheater, then sensible heat in air will be corresponding to epsilon into H POC and 1 minus epsilon H POC will be exiting. This is our furnace. This is the fuel input. This is the air. So, this is how now the balance look like this. Now, in this situation when we are say recouping the heat and transferring into the furnace, then two possibilities arise. Then we have two possibilities. We can think of two possibilities. Say in one we keep say fuel input, we keep fuel input is H in as in equation 1. That is, we are not changing the fuel input. In other way, we are not changing the heat input. If epsilon is the preheater efficiency, then epsilon into HPOC is the heat recouped and sent back to the furnace. So, if you write down again the steady state heat balance, write down steady state heat balance, then steady state heat balance is H in plus epsilon H POC, that is equal to H dash U plus H POC plus H L. Now, since Tu is to be kept constant, when we supply addition amount of heat into the furnace, the temperature of the furnace and hence the temperature of the product is not, should not change it. That is the first condition. When this happens, then TPOC will not change. Could you get me? What I am trying to tell you is that by supplying extra amount of heat into the furnace, the temperature should not change, because that is our requirement. The product should be heated at temperature Tu, on which we have made the balance in equation 1. So, if the temperature does not change, then TPOC will also not change, TL will also not change. Then what will happen to the additional amount of heat which you have supplied into the furnace? Then all the additional amount of heat will be used to heat the extra amount of product. So, that means here H dash U, that will be equal to H U plus epsilon H POC. So, now we redefine thermal efficiency, that will be equal to H U plus epsilon H POC upon H in, that will be equal to thermal efficiency original that we have defined plus epsilon H POC upon H in. So, the addition of extra amount of heat when fuel input is not changing, temperature should not change, then it will lead to increase in thermal efficiency of the furnace. In another possibility, let us think another situation. In another situation, what another situation could be? We are using the same amount of load, we are not increasing the amount of load. In that case, what will happen? The extra amount of heat that you have supplied into the furnace, that will increase the temperature. But that should not happen, because our condition is that the furnace should operate at constant TU, which was attained by constant TAFT adiabatic flame temperature due to the products of combustion. So, when the product amount is not changing, and if we add extra amount of heat, that will lead to increase in temperature which should not be there. So, in that case we have to cut down the fuel input. When we cut down the fuel input, then again the entire situation of the furnace, the entire temperatures will again remain the constant. So, in this case heat balance, that is in situation when product or the amount of product is not increasing. Also top of the condition is the furnace temperature should not increase. So, in that case the heat balance at a steady state for this situation would be, say, H in plus epsilon HPOC, that is equal to HU plus HPOC plus HL. Now, since TU and TPOC is to be kept same, so fuel input must decrease. So, therefore, H in, that will be equal to H dash in plus epsilon H into POC, and H in minus H dash in, that is equal to fuel saving due to preheater installation. Due to preheater installation, and that will be equal to epsilon H POC. So, that is what the concept of thermal efficiency and as affected by the installation of preheater. So, that is how this this quantification of thermal efficiency can be done this way. Now, another thing is that the carbon credit or carbon offset and its interrelation with energy efficiency. Now, let me define what carbon offset means. A carbon offset is a financial instrument aimed at a reduction of greenhouse gas emission. Greenhouse gas emissions. That is what a carbon offset means. Now, carbon offset is measured in terms of metric ton of CO2 equivalent. That means one carbon offset that is equal to reduction of 1 metric ton of CO2 or its equivalent in other greenhouse gases. Now, again 1 metric ton of CO2, 1 metric ton of CO2 reduction is equivalent to reduction of 270 kg of carbon. That means, if we want to generate 1 carbon offset, we have to reduce 270 kg of carbon in our process by making the furnace more energy efficient. Now, reduction in carbon, it depends upon how efficient the furnace is. One of the example, there are several ways to generate the carbon offset. The ways to generate carbon offset, all that you have to reduce the amount of carbon that is going into furnace. So, one way is that using renewable source of energy. One way is to use renewable source of energy, and another is reduction in fossil fuel consumption. Reduction in fossil fuel consumption, and it is in this connection the energy efficiency is a very important. One way is to recuperate the heat. Just now we have seen and used to preheat the air. So, in this case we have seen that fuel saving, if we recuperate the heat of the waste gases and used to preheat the air, then just now we have said that is fuel saving, that is equal to epsilon H POC upon H in into 100, that is in percent. Now, let us say if H POC upon H in, let us say equal to 0.5 at 1240 degree Celsius and epsilon is equal to 0.3, then fuel saving is 15%. And from there, depending upon the data on the available fuel consumption, one can calculate the carbon offset and so on. Now, this whole concept I will be illustrating by solving a problem. So, let me illustrate whatever I have said in this particular lecture through a problem. So, let us consider a continuous furnace. Say consider a continuous furnace to reheat billets from 298 Kelvin to 1400 Kelvin for thermomechanical processing. The billets enter and exit at 13 tons per hour. Now, the furnace is oil fired. The composition of oil is 85% carbon, 14% hydrogen and 1% sulfur. 25% excess air is used, 25% excess air is used. The fuel rate is 100 kg per hour and its net calorific value, that is equal to 40,000 kilojoule per kg. The POC exit at 1500 Kelvin. Now, this is the problem that I have selected to illustrate thermal efficiency, furnace efficiency and so on. Now, say calculate heat loss and thermal efficiency. Heat loss and thermal efficiency. So, now let us proceed to solve the problem. Now, for example, the furnace looks something like this. Is a belt on which there is a continuous discharge of the billet enters and exits. This is the burner. This is another burner. See, somewhere here there is a billet in, here POC to stack, here your billet, they are moving continuously and here billet is out, here supply is fuel and here supply air, same thing here fuel and top we supply air. So, the products of combustion they move and ultimately they out. So, it is a counter current process in which the billet and products of combustion they move opposite to each other. Well, we have nothing to do with the process, but since there is a continuous process and you know, and these are the so called billets. This is the exit of the billet and this is the exit of POC. So, let me represent this problem by a block diagram which is like this. Here say billet out, here POC exit, here say billet in a furnace which is at 13 ton per hour and heated to 1400 Kelvin. So, billet out and POC exits at 1500 Kelvin. At 1400 Kelvin, now this is supplying oil of composition 85% carbon, 14% hydrogen and 1% sulfur. Combustion condition 25% excess air. That means, total amount of air is 125%. Now, this is a steady state block diagram to solve the problem. Now, this is the way I solve, you can generate your own style of solving, that is up to you. Now, you also require certain values. So, I am giving you also certain values. Say for example, you require the heat content of the billet, because when you do the heat balance, so I am giving you certain values. Say H 1400 minus H 298, that is equal to 10120 upon 4.183, that is equal to 2419 kilojoule per kg mole. Then H 1500 minus H 298 for CO2, that is equal to 14780. This is in kilocalorie per kg mole. For H2O, that is equal to 3168, this is H 1500 minus H 298, then H 1500 minus H 298 for SO2, that is equal to 3724, and H 1500 minus H 298 for O2, 9711, and H 1500 minus H 298 for nitrogen, that is equal to 9186. Now, in fact, these values you should be able to calculate by CPDT by integrating. For example, if you want to know the heat content in steel, if you integrate CPDT from 298 to 1400 Kelvin, use the value of Cp, A plus Bt and so on. Similarly, the products of combustion you have to calculate from Cp, but here I am giving you the calculated values, but for solving the problem you have to calculate so on. So, once these values are before you, now we can proceed to calculate. For example, first of all we have to calculate heat taken by billet. Heat taken by billet, that is straightaway calculation, that will be equal to 13,000 upon 55.85, this is the moles, into 10120 upon 4.186. So, that is equal to 5.63 into 10 to the power 5 kilojoule per hour. So, that is what the heat taken out by the billet. Now, next we have to calculate the composition of the fuel oil is given, 25% excess air is being used. So, you have to calculate the composition of the products of combustion. That exercise that you do it, and the fundamentals I had already covered in my lectures on combustion. So, I have calculated straight away. So, POC, now do not forget, since we are using excess air, so the POC will also contain oxygen. So, that is an important thing. So, POC CO2, that will be equal to 7.083 kg mole per 100 kg of fuel. Then H2O, that will be equal to 7 kg mole, SO2 0.03125 kg mole, O2 2.653 kg mole, and nitrogen, that is equal to 49.885 kg mole. Now, mind you, all these are based on 100 kg fuel. So, what we have to do now? You have to multiply now this kg mole with the heat content that I had already given you earlier, H 1500 minus H 298 for CO2 was 14,780. So, I multiply each values and I sum total, then I get heat to POC, that is equal to 2.6 into 10 to the power 6 kilojoule per hour. Now, we know now if we see this particular block diagram, and if we do the heat balance, then heat input, that is equal to heat output by the billet and heat taken by the POC. So, what we will have to do now? We have to do now the heat balance. We have to perform now heat balance, and in the heat balance, heat input that will be equal to heat to POC plus heat to billet plus losses. Now, we have to determine the losses. So, heat input, the 40,000 per kg multiplied by 100 kg, 40,000 is the net calorific value and we are burning at a rate of 100 kg per hour. So, heat to POC we have calculated 2.6 into 10 to the power 6 plus heat to billet we have calculated 5.63 into 10 to the power 5 and plus losses. So, easily we can determine the losses. So, the losses would be from here, that will be equal to 8.37 into 10 to the power 5 kilojoule per hour. So, this is the answer for one particular problem. Now, I will suggest you please calculate yourself without seeing the solution, that will help you more. Now, we can calculate the thermal efficiency. See, thermal efficiency that will be equal to 5.63 into 10 to the power 5, that is heat taken by the product, heat in, that is 4 into 40,000 into 100 multiply by 100. So, that will be coming around 14.1%. So, you can see now from here that only 14% of the heat which is supplied by the fuel is used to heat the product, and that is important. And as in the initial lecture I have said that for the fossil fuel fired furnaces, a large fraction of the energy is taken by the products of combustion. So, you are seeing in this particular solution of the problem that thermal efficiency is only 14%. In many, if you calculate for other cases also, the thermal efficiency of the furnace without preheating, it hardly exceeds 15 or 20%. It remains more or less between 14 to 20%, because major amount of heat is carried away by the products of combustion. So, it suggests, as I have said in my initial lectures, that the recouping of the heat from the products of combustion is a very important part of the fossil fuel fired furnaces. In this case, in general, wherever fossil fuel is used and the temperature involved are high, then the products of combustion will leave at high temperature and heat recovery becomes a very crucial in order to optimize the fuel consumption. Now, in these connections, for example, if we calculate the furnace efficiency, we can also calculate furnace efficiency. So, furnace efficiency is, that is equal to heat in minus heat loss. Again, I emphasize this heat loss is through the lining and other losses, it has nothing to do with the heat taken by POC, divide by heat in. into 100 of course for percentage, then it will be heat in 4 into 10 to the power 6 minus 0.837 into 10 to the power 6 upon 4 into 10 to the power 6 into 100. So, this is equal to 79.1%. So, you can see now, as I said in the lecture, that furnace efficiency is much higher than the thermal efficiency. You are seeing here the furnace efficiency is of the order of 4 to 5 times higher than the thermal efficiency. Now, the whole whatever calculated we can represent in the form of a diagram, which is known as energy flow diagram, or you can also call as a Sankey diagram. Now, say if I take now, say this is the reheating furnace, this is the reheating furnace, and this one is a calorific value of fuel that is equal to 4 into 10 to the power 6 kilojoule, that is in. Now, out of which say this is how the energy is flowing. Now, say part of the energy is lost. This is the one 0.84 into 10 to the power 6 kilojoule loss. Say heat taken by steel, again a very small fraction, that is 0.56 into 10 to the power 6 kilojoule, and the major fraction, that is this is the 2.6 into 10 to the power 6 kilojoule is taken by heat to POC, and that is heat to steel. So, this is how it represents how the energy is flowing into the system. Now, suppose we install a preheater. Say we install a preheater and we recoup the thermal energy. There will be fuel saving, because we are keeping heat loss and we are keeping now heat loss and heat to steel same, and heat to steel we are keeping same. So, there will be naturally fuel saving. So, first you have to calculate the fuel saving. So, you please calculate by performing the heat balance. So, the fuel, now you require the fuel when we recoup the heat, and let us consider the preheating efficiency epsilon, that is equal to 0.5. So, now the fuel required would be only now 51.85 kg. You can see you are saving at least 49 kg of the fuel by recouping the heat. So, heat to flue gas we can now calculate, heat to flue gas. We can also calculate heat recovered and heat of combustion. So, heat to flue gas 1.35 into 10 to the power 6, all these values you have to calculate. I am simply writing the calculated value, that will be 0.67 into 10 to the power 6 kilojoule, and heat of combustion, since you are now combusting less amount of fuel, that will be 2.07 into 10 to the power 6 kilojoule. Now, the entire this furnace with the preheated system can be represented by an energy flow diagram in this particular way. Now, for example, if you consider this is a furnace, this is a furnace and this is where here we have the heat exchanger. This is the heat exchanger. So, now this is the calorific value of the fuel, which is now 2.07 into 10 to the power 6 kilojoule. Now, out of which here the heat losses 0.84 into 10 to the power 6 kilojoule. Steel is taking 0.56 into 10 to the power 6. This is to steel, this is to losses. And now, what we are doing is that we are now taking this heat to a heat exchanger, and this amount of heat is 1.35 into 10 to the power 6 kilojoule. This is our heat exchanger. We are taking this heat to the heat exchanger, and from the heat exchanger we are recouping the heat. So, this heat is 0.67 into 10 to the power 6. This is the recovered thermal energy, and the rest, that is 0.67 into 10 to the power 6. This is the flue gas to stack. Now, this is the energy flow diagram. When preheater is installed. So, this particular diagram indicates very clearly how the energy is flowing and what part heat exchanger is playing. So, you see a significant amount of energy is recovered, and the amount of fuel that you are saving around 49 to 50 kg, and that is a considerable value.